Okay, come back. Let us continue with our lecture. Currently, we are in the chapter on the Dirac equation and the quantization of. Thank you very much. The very thick, old-fashioned joint. Okay, very good. So we are in our section on the Dirac equation and the quantization of the Dirac field, and the last topic in our blueprint of what we always need to do in the canonical quantization procedure is to check what is actually the spin of the particles that we have created by this canonical quantization of the Dirac field. Therefore, we need to define our momentum and angular momentum and boost operators. In other words, we need to define the representation of our Poincare group on the Hilbert space of quantum states. And we have already begun by defining the energy momentum tensor and this tensor for the conserved current corresponding to Lorentz transformations and Lorentz invariants. And today we will from those define the momentum and angular momentum and boost operators. And then we can determine the Lorentz transformation properties of our created particles. And in that way, we will determine the spin, which will turn out to be 1/2, of course, but let us go through the details. So these were the expressions that we came up with the last time from the Noether theorem. These are conserved quantities. Rho is always the index corresponding to this conservation law. The zero component is the conserved charge or the charge density. And the spatial components are the current densities, and together they satisfy this usual continuity equation like the electromagnetic current. And so let us now define the corresponding Noether charges. Charges in quotation marks, because the charges correspond to conserved quantities like angular momentum and ordinary momentum and energy. So there is first of all the conserved quantity for translation invariance, which is the integral. First it's called P mu, the momentum operator, and it's the three-dimensional integral over the zero component of the T rho mu tensor. And then we have the conserved quantity for Lorentz invariance, which we call J mu nu, which is the D3x integral over this M0 mu nu. And both of those quantities are given here, so we don't need to copy it here. But in that way, we have defined expressions for conserved quantities. And on the classical level, if the equations of motions are satisfied, they will satisfy d by dt of that equals 0. And on the quantum level, we can now use those expressions and insert into the fields the field operators, and then we have defined operators which are defined on our quantum theory on the Hilbert space of states. And these operators will satisfy certain very good properties. Let us immediately write down those quantum level properties, which are analogous to the quantum level properties of those operators in the case of the scalar field, but they are of course a little bit more complicated. So, and we obtain quantum operators by simply replacing psi by psi hat in P mu and J mu nu. So what are those properties? The first property is again that these operators now satisfy the correct commutation relations for a representation of the Poincare group.
أنا يعني الحقيقة أريد أن أقول شيئا. هذه المعادلات هي مختلفة من المعادلات في الفيديو السابق. الفيديو السابق لهذا مباشرة تعطينا معادلات كونتراكتد بواسطة جي ميو أو جيرو جي ميو. نعم، فنجد أن بالنسبة للتي ميو تي روميو نجد أن رو فوق وميو تحت. أيضا نجد أن في الإم رو فوق وميو نيو تحت. هذا في الفيديو السابق. هنا الأمر مختلف. هنا هو استخدم معادلة كلاين جوردن أو تيار نيثر بالنسبة لمعادلة كلاين جوردن. لا أعلم حقيقة لماذا استخدم هذا. ربما من خلال هذا الفيديو يغير الموضوع ثم يذهب إلى التيار الخاص بالفيرميون، لكن الآن هو يتحدث عن تيار خاص بمعادلة كلاين جوردن اللي هي سبين زيرو. فمن هنا نعرف أنه ربما سيتعرج بعد ذلك إلى تيار الفيرميونات، أو أنه من هذه المعادلات مباشرة يحسب تيار الفيرميون. لهذا يجب أن نضع بالنا بجدية في هذا الموضوع ونركز عليه.
The first property is again that these operators now satisfy the correct commutational relations for a representation of the Poincaré group. And in the case of the scalar field, I think we have checked one example. Here we will not check any example in the lecture, but you are welcome to check all computational relations at home. It is simply plugging in all the known computational relations from the canonical quantization into these operators and into those expressions. Then you can explicitly verify that all the computational relations that should be valid are actually valid. Second, these operators here are Hermitian, just by their definition. They are Hermitian operators, and therefore the representation of our Poincaré group is a unitary representation, because that would be e to the I times those operators, and so therefore we have defined a unitary representation of the Poincaré group. And remember that this was a decisive necessary condition on a consistent relativistic quantum theory, and so that decisive condition is now satisfied. Third, the quantum field operator psi hat satisfies now a relationship in connection with this unitary representation of the Poincaré group. So let's give it a name here. So this defines a unitary representation u of lambda comma a, the same name as usually. And so now if we apply this operator in the following way, u dagger of lambda a, then a field operator psi hat at the argument lambda x plus a, so Lorentz transformed argument, and u of lambda a without dagger, then we get s of lambda times psi hat at x. A very complicated relationship, which, as we have discussed a few times also in the exercise, how many different representations of Poincaré are combined here. Here we have the standard Poincaré transformation of a 4-vector in space-time, x goes to lambda x plus a. Here, that is the 4x4 matrix-valued representation of the Lorentz group on the space of Dirac spinors, right? That's a numerical 4x4 matrix, and these matrices also satisfy the representation property for Lorentz transformations. And that is our unitary representation of Poincaré on the Hilbert space of states. It's a unitary operator. on an infinite dimensional vector space. So this representation, that representation, and this, they are combined here, and our field operator psi hat of x satisfies this relationship. And that you can check it by looking at the commutators for infinitesimal Poincaré transformation. So if you plug in infinitesimal transformations, then the left-hand side simply becomes a commutator of the field operator with those generators, and that can of course be explicitly evaluated because these operators contain psi and psi dagger, and we know all the commutation relations of psi and psi dagger. Therefore, this is explicitly calculable, and the result is this very nice form. Transformation inside simply becomes a commutator of the field operator with those generators, and that can of course be explicitly evaluated because these operators contain psi and psi dagger, and we know all the commutation relations of psi and psi dagger. Therefore, this is explicitly calculable, and the result is this very nice form, and that signifies psi hat as a Dirac field operator. So psi hat is a Dirac field operator. So, and again, I will not check this because this is all elementary. It's a few lines of commutation relations in all these cases. But now let us slowly progress to something interesting, and to continue, we now have to become a little bit more specific. Namely, we need to choose a specific basis of spinors of U and V spinors, which in other words means that we give a meaning to our index S. What do I mean? We have this sum always S equal plus minus 1/2 sum over U of P comma S times A of P comma S. This sum, right? This is an important sum which appears in our field operator psi hat. And so in the field operator there appears this, and there appears a similar sum with P dagger and V of P and S spinors. And we did not yet say what is actually the meaning of the index S. We only said S takes two values, and two values are clear because we knew that the spinors U, they have to be eigen spinors to the P slash matrix with eigenvalue plus M. There are two linearly independent eigenvectors of that kind. Therefore, we can label the two by some index S within values plus minus 1/2. Why not? This is at the moment just a label. But now let us define further properties of those two linearly independent spinors. There would be infinitely many possibilities, and all of those possibilities are equally correct. But we can now make a choice. Let us make a clever choice instead of an unclever one. And for this, let us go to some example. Let us choose the momentum parallel to the z-axis, or momentum equals 0 in the rest frame. If we have a massive particle, we didn't actually specify whether the mass is 0 or non-zero, but if the mass is non-zero, we can go to the rest frame. But if the mass is 0 or non-zero, doesn't matter, we can always choose a momentum in z direction. Let us choose such a momentum and then think about the meaning of the index S. So, how should we define our two linearly independent eigenspinors of the P slash matrix? We have then commutator of P slash with the Z spin matrix. That commutator is 0. Why is it 0? Because P slash now contains only gamma 0 and gamma 3, right? The momentum has an energy component, and it has maybe a 3 component, so that P slash contains only gamma 0 and gamma 3. Gamma 1 and gamma 2 do not appear in this sum. SZ is the commutator of gamma 1 and gamma 2 times I over 4. That is SZ. Okay, and then you see gamma 0 or gamma 3, they both commute with this product of gamma 1 and gamma 2. And therefore this commutator is 0, and that tells you from ordinary quantum mechanics you have two operators which commute, and therefore you can find simultaneous eigenvectors to both operators. So therefore our U spinors should be eigenspinors to P slash with some eigenvalue plus m. And so now a useful label would be that we define the two independent ones as eigenspinors of the Z-spin matrix, because that is for sure possible according to this relationship. And SZ is an explicit matrix with plus minus 1/2 on the diagonal. Therefore, the eigenvalues are plus minus 1/2, and so now that means that we should choose, or the useful choice is to define U of P comma S as the eigenspinors to SZ with eigenvalues plus minus 1/2. And therefore, we now choose SZ equal on P comma S equal plus S at times U of P comma S. And the same is of course true for the other spinors V, which have P slash V equal minus M times V. They can also be chosen simultaneously as eigenspinors to spin Z. But now a trick comes, so let us choose here minus S times V of P comma S. And in both cases, S equal plus or minus 1/2. So, and this is just my choice. You will soon see why it is a useful choice, but anyway, it's clear that, again, for V, you have two linearly independent ones, which can be chosen as eigenspinors to SZ with the two eigenvalues plus minus 1/2, and I just reverse the meaning. So if you have here plus 1/2, it has the eigenvalue minus 1/2, just to confuse you. But it also has some advantages. So, then, now, let us calculate something. Let us choose again P parallel to Z or 0. And let us now look at a specific type of Lorentz transformation. Namely, let us choose as a Lorentz transformation lambda a rotation around the Z-axis. So that symbol just means let us choose a rotation around the Z-axis with some arbitrary angle. Then we know a Lorentz transformation of our 4-vector P gives us in general a new 4-vector P prime. But in this case, if you rotate a vector which is in the Z-axis around the Z-axis, the vector stays the same. Therefore, in this particular case, lambda P is equal to P itself. The whole 4-vector stays unchanged. So this Lorentz group is an element of the little group in our language that we introduced some time ago. So let us consider such a Lorentz transformation in the little group. Then, if we apply this relationship here, this third one, with a complicated Lorentz or Poincaré transformation of the field operator, we can now write this down in the following way. U of lambda, let's only use a Lorentz transformation, and this particular Lorentz transformation, U of lambda, times the field operator, lambda x, times U of lambda, is equal to S of this specific Lorentz transformation, which is a rotation around the Z-axis. And let us now imagine our field operator is a Fourier integral with this dp tilde and a sum over S containing such terms. And then again, this equation must be valid for each Fourier mode, and it must be in particular valid for the Fourier mode in front of that sum on the upper blackboard. And that means that we get Q dagger of RZ times sum over S, U of P comma S, A of P comma S, U of RZ equal, and now we have here S of this rotation around the z-axis times the same sum, U P comma S, A of P comma S. So that just means that the equation must be valid for each Fourier mode individually, and that is one Fourier mode. And in principle, I would have here lambda x that translates into lambda p, so I would have here in general p prime, but p prime is equal to p, so we have here the same p on the left hand side as we have on the right hand side. Then what is this u of RZ? That is actually e to the minus I some angle theta z times our representation operator jz for angular momentum in the z direction. That is this, and this s is e to the minus I theta, the same theta angle, times our sz 4x4 matrix. So, and now we discover that since we have chosen our spinor u of p comma s as an eigenspinor of the sz matrix, we know how that transforms under the matrix S, because that is an eigenspinor, so it just becomes e to the minus I theta z times the number S. Okay, and then it would be in the sum. And here you get e to the minus I, this operator from the right, and the same operator with plus in the exponent from the left. And then you can look at the entire equation for infinitesimal angles theta. Then what happens to the left-hand side? On the left-hand side we get the commutator of the expression here with the operator jz. The commutator only does something with the operator a, because that is an operator while that is a number. So here we get the commutator of A with jz. On the right-hand side, we get the eigenvalue S times the spinor u of p, and the operator stays what it is. And so therefore, we can now read off what is the commutator of A of p comma s with the full angular momentum operator jz on our Hilbert space of states. And the result is our index S times the same operator A of P comma S. And so here I've also removed the sum and the spinor, because in the end the equation must be valid again for each linearly independent spinor. And so I can read off the coefficient of each spinor for each value of S, and then I obtain an equation which is just an equation for the angular momentum of this creation or annihilation operator A of P comma S. Good. Now the same can be repeated for the operator B involving the spinor V, which has the opposite side, the sign. In the case of B, something similar happens, but I would get here B dagger, and here I would get minus S because of that. But here I can also convert this relation into a relationship with A dagger instead of A by daggering the whole equation. Then I get also here a minus, and then the equations for A and B become the same. And so now I will just write down the general result. In general, we obtain now the following, all written in a uniform way. Jz with A dagger of P comma S, this commutator. This is now plus S times A dagger of P comma S. So you get that directly by daggering the previous equation. And similarly, JZ commutator with B dagger of P comma S also gives plus S times B dagger of P comma S. And here I get a plus because of that choice of the minus here before. The relative plus minus comes because in one of the terms I have A, in the other I have A dagger. And in order to make it uniform, I need the relative minus. So and these equations tell you what is the spin, or in general the angular momentum of the particle states created by A dagger and B dagger, because if you now create out of the vacuum a one particle state, then this tells you what is JZ operator applied onto that state, namely plus S.
لاحظ أنه هذه المعادلات يعني تم تقديمها في شرط واحد، هو أن الكميوتيشن بين البي اللي هو المومنتوم والجي يساوي زيرو. البي سلاش الكميوتيشن بين البي سلاش والاس زد يساوي زيرو. طيب إذا كان لم تساوي زيرو، هذا يعطينا أن البي سلاش والاس يعتمدان على الكتلة. فبالتالي هنا نرى أن المعادلة أو النتائج التي سنتحصل عليها هنا بعد أن يستقر الجسيم، بعد أن يستقر يعني على طول تحولاته في هذا الفضاء الصغير، فإننا لا نعتبرها حتى أن يعني يصبح فري بارتيكل ويسير في الفضاء موحد الخواص، موحد معادلات تدفق المكان والزمان. هنا نجد أن البي والإس commute with each other، لكن قبل ذلك not commute، وهذا ما لا تعرفه ميكانيكا الكم أو نظرية المجال الكمي.
And S is plus minus 1/2. Let's just write a few more words. You can do it similarly for general momenta which are not necessarily in the Z direction. There we can choose the following. We can take the spin vector and project it onto the momentum axis. This projection is called helicity. This is the helicity of the particle, the spin in momentum direction. And here in that case, that was simply the spin in Z direction because the momentum was already oriented in Z direction. So that was already helicity. But in general, you can always take helicity and that always commutes with P slash. Let's not prove it, but that always commutes with P slash, and therefore you can always choose the spinors such that that acting on U of P comma S is plus S times U of P comma S. So all the spinors can be chosen as eigenstates of helicity. And then this equation is modified similarly. If you choose that, then A dagger and P dagger create particles of helicity S, which is either plus or minus 1/2. Okay, and then let me just write down some more explicit equations. So you can now create a one particle state out of the vacuum by applying this A dagger of P comma S. That would be, let's say, a fermion F, let's call it F for fermion, with momentum p and helicity s, where again p0 is an abbreviation for p vector square plus m square. So it is a particle with helicity s and energy momentum relation such that the rest mass is m. Similarly, B dagger of p comma s acting on the vacuum gives you an anti-fermion with momentum p and s, the same energy momentum relation, and s in all cases is the helicity. Then, as the final word, let me also connect to something that is written in the Spinor script. There is so-called wave functions, which you can now construct. Namely, if you have such a one-particle state, you can build the following matrix element: vacuum on the left, then a field operator psi hat of x, and then your particle state fermion p comma s. What is the value of that matrix element? So here we have acted on the vacuum with a dagger. The field contains a without dagger and b dagger. Which term out of so this contains a and b dagger? Which of the term contributes? Both or none or one of them? So here that would be a dagger on the vacuum. Then only the a contributes, and the b dagger gives 0 because b dagger acts to the left onto the vacuum. That is the same as b acting on the vacuum, that is 0. So that gives 0, and the a contributes. A dagger, that gives always this typical normalization factor 2 pi cube times 2p0 times the delta function. And so therefore in the integral, the dp tilde integral gets cancelled, the sum over s gets cancelled, and the only thing that remains is the coefficient inside of the field operator in front of the component with this momentum and that spin s. And that is then e to the minus I px times the spinor u of p comma s. So this matrix element here, between a one-particle state, the field operator, and the vacuum, reconstructs for you this spinor u of p comma s. So you see that spinor has an interpretation. It describes an incoming fermion with a certain momentum and spin. Similarly, you can do it for an antiparticle with psi bar anti-fermion p comma s. Okay, so here you act with b dagger onto the vacuum, and psi bar contains b and a dagger. Then of course only the b contributes and the a dagger cancels, and we get similarly e to the minus I px times the spinor v bar of p comma s. And so the matrix element has here on the left a state of an anti-fermion, so that would be something like an initial state with an anti-fermion, and so therefore in Feynman diagrams later on, an initial state fermion will be accompanied with such a wave function u of p comma s, and an initial state anti-fermion will be accompanied with v bar of p comma s. And so you can also read about all these things in the Spinor script, where there is, in more colloquial language, where this is all summarized again. Okay, so this ends our blueprint discussion of the fermions. Okay, we have now completely analyzed the physical meaning of our Dirac field quantization. And here we see that we describe spin 1/2 particles, or helicity plus minus 1/2 particles. we have constructed the Poincaré representation, therefore it's a fully relativistic quantum theory with very explicitly clarified physical interpretation. Any questions?
For exactly the calculation, we saw that it was 1/2.
We first of all saw that our spinors u of p comma s, they had to be introduced, and they okay, sorry, let me back up. So okay, so here the main thing is the commutator of our creation and annihilation operators with a full angular momentum operator of the theory, so that is what we need to evaluate. And during the evaluation, in intermediate steps, a field operator appeared. This contains our spinors u of p. They are eigenspinors of this SZ matrix, and this matrix has eigenvalues plus minus 1/2. And this eigenvalue plus minus 1/2 of the spinors, this propagates into this equation for the commutation relation with a full angular momentum operator. Therefore, the particle states created, they have really angular momentum in a certain direction here of plus minus 1/2. That is a necessary consequence of the representation, because how did this SZ 4x4 matrix with eigenvalue plus minus 1/2 appear? It appeared because the field operator satisfies this relationship where that representation appears. And so, of course, in this way you see clearly the connection to the very beginning, because, of course, we started with saying we want to analyze a field which is this 1/2, 0 or 0, 1/2 representation of the Lorentz group. That was the starting point, and that immediately gave rise to this representation of the Lorentz group, which automatically has eigenvalues plus minus 1/2. That is the construction principle of this 1/2, 0, 0, 1/2 representation of the Lorentz group. So that is where the 1/2 initially came in. And that, of course, propagates through the entire construction. And it's no surprise that in the end, the eigenvalues of those matrices appear in the commutation relations. But the starting point was that we wanted to have a field which transforms in this 1/2, 0, 0, 1/2 or Dirac representation of the Lorentz group. And this recipe of canonical quantization, one should really consider it as a recipe, is a recipe which preserves this initial property throughout the entire formalism. Okay, other questions? Yep. There is a difference between p slash and p square. So clearly the spinor v, it satisfies p slash v equal minus m times v. But on the other hand, the p, which is inside this, satisfies p mu equal plus m square. That is always true. So, and there is no contradiction between these two equations. And in our field operator, the important thing is the dp tilde integration measure, which makes sure that this relationship holds, including the sign. So this measure contains the requirement that P0 is positive. And that is, of course, by the way, a difference between our quantum field theory formalism here, where we always have manifestly positive energies, and some treatments of the Dirac equation in relativistic quantum mechanics, where sometimes negative energies pop up in some calculations. Here, there are no negative energies anywhere in our calculations. They are manifestly avoided by this construction. And on the other hand, we obtained this requirement that we need simultaneously positive energies and positive norm of our states in the Hilbert space, and that gave rise to Fermi statistics, right? So this inconsistency of these treatments where you have negative energy, they are visible in our formalism by this potential disaster of negative norm states if we would choose the wrong bosonic statistics instead of the correct Fermi statistics. Right. Other questions? Good. Then let us nevertheless go on with the Dirac field a little bit more before we come to the next topic. I have two more sections on the Dirac field, and we should do them both today. They are fairly short, but there is a lot of technicalities to be said about the Dirac field which are important for physics. So, two sections on additional information on Dirac fields. The first is charge conjugation. So, we specifically choose here a certain representation of the gamma matrices which satisfies the following, namely the Hermitian conjugate of gamma mu should be gamma mu, gamma 0, gamma mu, gamma 0. What does that mean? It means that gamma 0 is Hermitian. Gamma 0 is Hermitian because then you have gamma 0 dagger is equal to gamma 0, gamma 0, gamma 0 is equal to gamma 0. And all the other gammas are anti-Hermitian because for all the others you have gamma I equal gamma 0, gamma I, gamma 0, which is minus gamma 0, gamma 0, gamma I. Gamma 0 square is 1. So all the other gammas are anti-Hermitian and gamma 0 is Hermitian. And we assume gamma mu star complex conjugation is equal to gamma 2, gamma mu, gamma 2. That means gamma 2 is imaginary and gamma 2 star is minus gamma 2 and all the other gammas are real. And then also the Z spin matrix, which is the commutator of gamma 1 and gamma 2. Gamma 2 is imaginary, gamma 1 is real, and it has an I, so this would be real as well, as Z star is equal to SZ. And all these equations are valid in most normal representations. That is valid in the so-called Dirac representation, Weil representation, and some other well-known representations. So this is nothing special to satisfy. But let's go on specifically for this case. And then we define a matrix capital C is defined as I times gamma 0, gamma 2. So this combines this like Hermitian and complex conjugation. And then we define for each Dirac spinor psi, we define an object psi with a superscript C, which is supposed to mean the charge conjugated spinor is defined as that matrix C times psi bar transposed. Okay. What is psi bar transposed? Psi bar transposed is the same as C times psi dagger. Gamma 0 transposed is the same as C times gamma 0 transposed times psi star complex conjugated. That is the same as gamma 0, and then you can plug in that matrix C, gamma 0 anti-commutes with gamma 2, gamma 0 square is the unit matrix, so that is the same as minus I gamma 2 times psi star. So the charge conjugated spin or psi superscript C is defined in this way, either in that way or in this way, they are equivalent. And then let us discuss what that definition means. Why do we call it charge conjugation? We call it charge conjugation because of two very fundamental and interesting properties which I want you to know. So first of all, if you have the following equation, that was actually an exercise in our quantum theory lecture that some of you have attended. ID slash minus m Dirac equation, but now an interaction term plus E times A slash acting on psi equals 0. That is a Dirac equation with interaction with an electromagnetic field A, and that whole object here is a covariant, gauge covariant derivative minus m, but that is all not important here. But you see the interaction with the electric field is governed by an electric charge prefactor plus E. So if that equation is valid, then, and that was your exercise, automatically the following holds: ID slash minus m minus E times A slash acting on psi C is also satisfied. So that is equivalent. If psi satisfies the equation with plus, psi C satisfies the same equation with minus, and so you see that the charge reverses its sign, and that motivates the name charge conjugation.
طبعا هنا في معلومة مهمة جدا جدا، وهي أن الشحنة سواء كان سالبة أو موجبة تتفاعل مثل الجاذبية، ونحن نعلم أن الجاذبية لا يوجد جاذبية سالبة وجاذبية موجبة، وبالتالي الشحنة سالبة أو موجبة تتفاعل بنفس الطريقة التي تتفاعل بها الجاذبية، ومع تغيير صاي، وهي عملية رياضية بحتة. لكن في النهاية نجد أن الإلكترون عبارة عن كتلة لديها جاذبية، والبوزيترون عبارة عن كتلة لديه جاذبية ونفس الجاذبية إلا إذا اختلفت الكتلة. نجد أن الشحنات هنا أيضا لديها نفس التكنيك، ليس نفس الخصائص، فقط في شيء واحد، وهو أن إذا تقارب إلكترون وبوزيترون فإن الشحنات تحاول أن تلغي بعضها في موضوع الجاذبية، في موضوع التحدي للفضاء صناعي بعض غير متناظر، أما الكتلة فلا تلغي بعضها البعض. وهذه آلية كما ذكرت في الفيديو السابق أنها آلية فعلها الفضاء صناعي الأبعاد لكي يتخلص من الشحنة، ولكنه بعد لم يستطيع التخلص من الجاذبية أو الكتلة، لكن استطاع أن يتخلص من الشحنة أو على الأقل يخفي خصائصها. وهذا بعد في الكوارك، كوارك وأنتي كوارك يمكن أن يحتوى داخل مساحة ضيقة جدا جدا وتسمى متر وأنتي متر، حيث أنه الكوارك والأنتي كوارك لا يستطيعان أن يلغيا بعضهم البعض، اللي هو في جزيء يسمى البايون أو الميزون. فهذا الجزيء يحتوي على الكوارك وأنتي كوارك، هذان الجسيمان أو الكوارك أنتي كوارك يعيشان مع بعضهم البعض في سلام. هذا بسبب أن الفضاء صناعي الأبعاد استطاع أن يفعل أو استطاع أن يحمي نفسه من الشحنة، لكنه لم يستطع أن يحمي نفسه من الكتلة، فالكتلة تسبب تهديدا للفضاء صناعي الأبعاد. لكن من خلال الشحنة يمكن للكوارك والأنتي كوارك أن يتواجدا مع بعضهم البعض في هذا الفضاء الصغير جدا جدا، وربما استطاعت الشحنة أن تؤدي أو تؤثر على الكتلة، ربما استطاعت الشحنة أن تؤثر على الكتلة. بهذا نجعل أنه نظرية الكونفاينمنت أنه كلما تقارب الجسيمات مع بعضها البعض كل ما تصرفت كفري بارتكلز، وكل ما ابتعدت عن بعضها البعض تصرفت كباوندد بارتكلز. إذا الشحنة أثرت على الكتلة بطريقة ما، ولكن بشرط أن الشحنة يجب أن تكون مع مضادها. طيب تعال نواصل.
So I don't know whether we should prove that. Should we prove that? It was your exercise, so you can prove it at home by looking up the old exercise sheet. Let's look at something else. And if P slash on the spinors U is equal to MU and spin Z, SZ acting on U equal SU, and P slash V is equal to minus M times V, SZ V equal minus S times V, that was our condition, then you can show that the charge conjugated versions of U and V, they satisfy the following. P slash UC is equal to minus M times UC S Z UC is equal to minus S UC, etc. So that you see that lo and behold, the charge conjugated U is equal to V and the charge conjugated V is equal to U with the same arguments. So let me add, in general, this is valid up to normalization, because of course if I require some eigenvalue equations, the spinors are fixed only up to some normalization. But if I choose a clever normalization, then we have really the equality here. And that is the normalization that I've chosen in the spinor script. So
طبعا هذا ما يحقق الكلام الذي ذكرته قبل قليل، حيث انه لا conjugation يساوي انتي متر بالنسبة لليو تعطينا الفي، والعكس تماما الكونجيجيشن بالنسبة للشارج كونجيجيشن يعطينا الجسيم الآخر، لكنهما لديهما نفس الكتلة لكن يختلفا في الشحنة، والشحنة تؤثر على الكتلة بطريقة ما بحيث أن تجعل هذه الجسيمات تتقارب مع بعضها بكل أريحية إلى حد ما. إذا تقاربت الجسيمات اللي هو كوارك وأنتي كوارك بدرجة كبيرة فإن الفضاء ثنائي الأبعاد ويفعل آليته مباشرة. يجب أن يكون مستواهما في درجة معينة بحيث أن الفضاء ثنائي الأبعاد لا يفعل آلية الدفاع عن النفس، لكن أقل تقارب أكثر الفضاء ثنائي الأبعاد يفعل الآلية، وأكثر تباعدا الفضاء ثنائي الأبعاد يفعل الآلية.
this is exactly valid.
ولاحظ آلية الفضاء ثنائي الأبعاد بالنسبة للتباعد أنه يخلق أنتي متر تاني، يعني كوارك يخلق أنتي كوارك مرة أخرى. إذا بعدت كوارك أنتي كوارك من بعضهم البعض فكل كوارك يخلق أنتي كوارك، وكل أنتي كوارك يخلق كوارك. هذا بسبب أن الأفضل في الطبيعة أن يوجد المتر وأنتي متر أو الكوارك وأنتي كوارك مع بعضهم البعض، مثل أن الأفضل في الطبيعة أن يوجد الجزيء مع بعضه ولا الذرة. يعني نحن نجد أن الهيدروجين يوجد في شكل جزيء لا يوجد في شكل ذرة، هذا يعني أن الذرة تعاطى أعلى من الجزيء، وناتج من أنه اللي هو الإلكترونات تتقاسم المدارات والإجهاد الذي يحصل في الذرة بسبب سرعة دوران الإلكترون حول البروتون، نجد أن الإلكترون يأخذ مساحة أكبر في حالة الجزيء، وبالتالي توجد في الطبيعة في شكل جزيء. نجد الهالوجينات، نجد بعض الغازات في شكل الأفضل أن يكون في شكل جزيئات، على عكس المعادن الأفضل أن يكون في شكل الأكسجين في شكل جزيء. الثاني ماذا؟ نيتروجين في شكل جزيء. الصوديوم يجب أن يكون الأفضل أن يكون منفردا وهكذا. وهذا ناتج من الإجهاد الذي يفعله وجود هذه الشحن وسرعة الإلكترون مثلا، حيث يعمل سحابة إلكترونية حول الذرة. وأيضا الذرة، أيضا النواة الذرة أيضا تمثل نوع من الثقل، لكن عندما توجد في شكل جزيء فإن محاولة توسع الإلكترونات في المدار ككل، المدار الجزيئي، يجعل الأفضلية لهذا. وهذا هو سبب الفضاء النبعات يميل إلى هذا الأمر على عكس الذرات الأخرى. هذا الأمر ينطبق أيضا في الكوارك والأنتي كوارك.
For the normalization in the Spino script, which is of course also the normalization that we have always chosen here. And using these equalities here, UC becomes V, VC becomes U. You can now look at the final equality. Namely, if we have our field operator in the quantized theory, psi hat of x, then that was this dp tilde integral sum over s e to the minus ipx u of p comma s times a of p comma s plus the same with b dagger. U and A and V and B dagger. Then the charge conjugated field operator, where now charge conjugation means literally this thing here, or equivalently that, where if you put in an operator, that would mean that you take the spinor with its 4 operator components, and in each component you dagger it. Star becomes dagger, but for each component. So then, what happens? So if you dagger it, then A becomes A dagger, B dagger becomes B, but U becomes UC, which is V, and V becomes VC, which is U. And so therefore, here you get UC is V, here you get A dagger, so V will be accompanied with A dagger, and U will be accompanied with B without dagger. That means A and B are reversed. That's just the effect. A and B are simply reversed. They exchange their role. E to the minus IPX, U of P comma S, B of P comma S, plus E to the IPX, U, PS, and A dagger of P and S. So that's the simple rule. So simply A is exchanged with B entirely. That's it. And everything else remains. And so in that way, you of course also see once again that this charge conjugation operation exchanges particles and antiparticles in our interpretation of the quantized theory. So both of these issues, this one and that one, explain why we call that here charge conjugation operation. So, and the proofs are all obvious. So let us not waste time with the proofs. Do you want to see any proof? We might put in a proof in the exercise if you want, but I do not really, I see some. Okay. Good, that is what I wanted to tell you to charge conjugation. Yes, a question. To this one?
Where is it?
Okay. Yes. So I meant this equation here. So on the level of numbers, psi star is clear what it means. You take the complex conjugate of each component because that is a 4-component object. But what does it mean to say psi hat star? That is not really a defined operation. But what I mean, if I interpret this on the quantum level, is that we have here our psi hat, which is a 4-component object. Psi hat first component up to psi hat fourth component. And the star means, now you should write it as dagger and transpose. That means each component gets a dagger, but we do not get a row vector, you know. So psi dagger normally would be this, psi 1 dagger, comma, psi 4 dagger as a row instead of a column. But psi dagger transpose is this. That is simply the difference. And so on the level of operators, we should interpret this as psi dagger transpose. That is the interpretation on the level of operators. For numbers, it's the same. For operators, the star doesn't make sense. That is what I meant. Because here, the psi c has really the structure of a column spinor, of an ordinary spinor, which has this column shape. Good. Then the next topic on additional information, chirality. In particular, chirality versus helicity. So let us begin with helicity. Helicity, let's call it small h, is this p vector times spin vector divided by p vector magnitude. So it's the projection of the spin onto the axis of motion. So this is only defined if you first have specified a particular particle state with a definite momentum. And this is a quantity which is useful because we could organize our spinors u and v and the operators a and b according to eigenvalues of helicity. Clearly this helicity has eigenvalues plus minus 1/2. And our particle states created by a and b, they are at first eigenstates of helicity. So that is nice. And also experimentally, helicity is a nice concept. You can measure it, you can prepare particle beams with certain helicities. So it is a physical quantity. And let's just stress that it is experimentally accessible. Good, but it is not Lorentz invariant. Okay, why should it be? It's something connected to angular momentum. That's not necessarily Lorentz invariant, but let's just make it explicit. It's not invariant under certain boosts. let us imagine here our particle with momentum p in that direction, and the spin is like some rotation. For example, here a left-handed rotation, that should be a left-handed rotation, so this particle would be left-handed, has helicity equal to -1/2, so it turns left while it moves like that, has helicity -1/2. Then let us do a certain boost, and now we can do a boost which is such that the observer goes into the same direction as the particle, but it overtakes the particle. So it runs faster than the particle. Then, so the boost should overtake the particle. What happens if you overtake this particle? So you as an observer are now just moving in the same direction, the particle is left behind you, then the momentum of the particle just changes its direction. For you now the particle momentum is in that direction, but of course the particle still turns in the same way. It of course still turns in the same way. Therefore, if you now project the spin onto the axis of momentum, the rotation is the same, the momentum axis has reversed, so the helicity is now +1/2. So and that simply shows you that by overtaking the particle with a boost, you can flip the helicity, and therefore the helicity cannot of course be a Lorentz invariant quantity. There is only one exception when the helicity can be a Lorentz invariant quantity, and we have already discussed that in our analysis of the general Poincaré group and the little group of particle states, namely for massless particles. For massless particles, we have actually proven that the helicity is Lorentz invariant, and here it's clear that if the particle is massless, it moves at the speed of light, and no observer can overtake the particle. Then you understand that the helicity can be Lorentz invariant. So except for m equals 0. But in general, the helicity is not Lorentz invariant. Okay, so much for helicity. Yes? Yeah, it's undefined. It is undefined. And for our spinors, they would be defined in some convention. We would always use the convention: if you go to the rest frame, you treat the particle as if it would move with in z direction. So the spinors in the rest frame are organized according to spin z. That is just our convention. And also if you look at the explicit solutions in the spinor script, they are continuous if the particle goes to rest, and they converge to eigenstates of spin z. That is possible. You could also do other choices, but that's a possible choice. But helicity then is undefined. Now, however, let us turn to chirality. The concept of chirality is a specific concept for spinors. Chirality is a Lorentz invariant property of spinors. So it's not immediately a property of physical particle states or of physical states at all. It's a property of these Dirac spinors, these complex four-dimensional spinors. And so to define it, let us introduce finally the important matrix gamma 5. Gamma 5 is defined as the product of all the gammas. Gamma 0, 1, 2, 3 with upper indices, and by convention for gamma 5 we only use the lower index. And let me immediately write down what is the result in the Weil representation. You can check it. It's a block matrix which has here -1, 0, 0, +1, -1, 0, 0, +1. So a very simple diagonal block matrix with 2 by 2 blocks. And then we define projection operators P left. P left is 1 minus gamma 5 over 2. So, and what is that? 1 minus gamma 5 over 2 in this while representation. This would just be the block matrix 1, 0, 0, 0 with ones and zeros on the diagonal. Okay, so that is a projection operator which projects onto the first two components and it projects away the last two components. Then there is also a p-right projector, 1 plus gamma 5 over 2, which is then 0, 0, 0, 1 in while representation. So it's also a projection operator which projects out the last two components of your spinor. And then we have some properties which are representation independent. So always gamma 5 square is the unit matrix, and you can immediately see it from this representation, but it's valid in general, is the unit matrix. Then these operators PL, they are projection operators. That means PL square is equal to PL, PR square is equal to PR. This is called projection operator, such a property. And they are projection operators on orthogonal subspaces, namely P left times P right gives the zero operator or the zero matrix. And also P left plus P right gives the unit matrix. That is also obvious. So we have two projection operators onto orthogonal subspaces, and together they project onto the full space. Then the final very important property is gamma mu commutator with this new gamma 5, anti-commutator. That is 0. So gamma 5 anti-commutes with all the normal gamma mu matrices. So, and using this gamma 5, we can then define the notion of chirality, left-handed and right-handed handedness. And you see this already in these indices, P left, P right. They will be projectors on what we call left-handed or right-handed. So that is the definition. Eigenstates of gamma 5 are called chirality eigenstates. And eigenstates of gamma 5 are spinors. Gamma 5 is a 4x4 matrix in the space of spinors, and so the eigenstates are Dirac spinors or variants. And so chirality is therefore a property of spinors. Let us exemplify this a little bit with some relations. Let us take some general Dirac spinor psi, which is a 4-component complex spinor as usual. And then what can we do? Using all these new matrices, projection operators and gamma 5, we can first of all define a left-handed part of the spinor by projecting it with this P left. In while representation, it are just the first two components, and we annihilate the other two components. But in a representation independent way, you can always do this projection. And then you have something called psi left or left-handed spinor. Similarly, of course, psi right is equal to P right times psi. Then what do we have? So we always have the full spinor psi is the sum of this psi left plus psi right, because the two projection operators sum up to the full unit matrix. Therefore, that is an identity, and you can always construct from any spinor its left-handed and its right-handed parts. Further, let us act with gamma 5 on one of them. Let us act with gamma 5 on psi left. What happens? let us act with gamma 5 on psi left, and let us do this now explicitly. So we have skipped many proofs today, but let's do this proof explicitly. So this is p left acting on psi, that is p left. And now let's for once evaluate this. So if we evaluate it, we have here gamma 5 times 1 minus gamma 5 square divided by 2 acting on psi. What, however, is gamma 5 square? Gamma 5 square is the unit matrix. Therefore, we get gamma 5 minus 1 over 2 acting on psi. And what do we now have? That is, of course, minus the projector p left. So therefore, we get in the end that is equal to minus psi left. So if we define our left-handed spinor using this projection, then it becomes automatically an eigenspinor of gamma 5 with eigenvalue minus 1. So the psi left is a chirality eigenstate with eigenvalue minus 1. And similarly, psi right, you have here a plus, 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 plus. Then it would be an eigenstate of gamma 5 with eigenvalue plus 1. So let's write that down. Psi left and right are chirality eigenstates. Gamma 5 psi left or psi right is equal to minus or plus psi left or psi right. So for any spinor, you can always construct a left-handed and a right-handed spinor, which is a chirality eigenstate. So that is nice, and so that exemplifies that such chirality eigenstates really exist. And now let us continue to discuss why this is interesting and important, and for that let us look at Lorentz invariance properties. Lorentz invariance. The Lorentz transformations are governed by our spinor representation S mu nu, which is a commutator of gamma mu, gamma nu. And so now we have to ask, what is actually the commutator of S mu nu with gamma 5? 20 seconds of time for you to think. What is this commutator? If you remember that is I over 4 gamma mu gamma nu. So each term is a product of two gammas. And for each gamma, we know that one over there, gamma mu, gamma 5, anti-commutes. No. Right. So, just as a remark, it becomes increasingly complicated to always remember those product rules for commutators. So my strategy in order to evaluate things like this is always to simply start with the left-hand side of the commutator and then calculate until you end up with the right-hand side. So in this way, my strategy would be to start with that and try to bring the gamma 5 step by step to the left with some intermediate steps. And so then I see that this is proportional to one term would be gamma mu, gamma nu, gamma 5. Let's just look at such a term. Then I know that I can bring the gamma 5 here and get a minus sign. So this would be minus gamma mu, gamma 5, gamma nu, okay, because of the anti-commutation rule. And then I can bring it once again to this place, and then I get plus gamma 5, gamma mu, gamma nu, and so then I see that this works for every term, and so I will get gamma 5 times S mu nu. So in this way, I see S mu nu gamma 5 is in the end equal to gamma 5 times S mu nu. And so this is a little bit safer to do it this way in cases where you have really products of many, many matrices, because that always works if you implement such a strategy and you do not need to remember which product rule you should apply. But anyway, you are right, and the commutator is indeed 0. What is the physics meaning of that 0? That has a physical meaning. Which physical meaning does it have? That is a generator for Lorentz transformation. So in general, full Lorentz transformations of spinors commute with gamma 5. That means if you have an eigen spinor of gamma 5 and you apply a Lorentz transformation, it remains an eigen spinor of gamma 5 with the same eigenvalue. So the chirality eigenstates, they are invariant under Lorentz transformations. So all the spinors with eigenvalue plus 1, they transform into each other by Lorentz. All the spinors with chirality minus 1, they also transform into each other by Lorentz transformations. And there is no mixture. You cannot Lorentz transform a minus 1 chirality spinor into a chirality plus 1 spinor. That doesn't work. So therefore, let's first write it down. Chirality is invariant under Lorentz. And by the way, this is now important here, so let me stress it. When I say Lorentz in this chapter here, I always mean the continuous Lorentz transformations which are connected to the identity. This does not involve time reversal, space reflection, and these sort of things. Only infinite Lorentz transformations which can be continuously transformed to the identity. Continuous Lorentz transformations. Under those, chirality is invariant. So that also means the Lorentz representation is reducible because there are two invariant subspaces. There is the subspace of spinors with chirality minus 1, which is invariant under Lorentz, and the other subspace of spinors with chirality plus 1, which is also invariant under Lorentz. So the whole space of spinors is decomposed into two subspaces, which together fill up the whole space, and the subspaces are each invariant under Lorentz transformations. Such a situation is what we mean by a reducible representation. Two invariant subspaces. Good. And so, since chirality is Lorentz invariant, it is obviously an important concept, an important thing to know about. And in particular, since the two Lorentz invariant subspaces are defined by their chirality properties, this is clearly an important thing to know. That is why I wanted to tell it, and there is a little bit more. So let us also write down some relationships for the barred spinors, the adjoint spinors. What happens to them? Take a left-handed spinor, psi L, and now, after making it left-handed, we bar it. Okay? So by this notation, I mean, because the order matters, we first project to left-handed, then we bar it. So that means literally we do p left psi, and afterwards we bar it. That means by definition we do p left psi, then we dagger it, and then we multiply by gamma 0. So what does that mean? So psi dagger, p left dagger, gamma 0. Okay. Good. So psi dagger is the same as psi bar gamma 0. Now what is p left dagger? In our assumption, it's already deleted, but we have assumed that only gamma 0 is Hermitian, all the other gammas are anti-Hermitian, and therefore gamma 5 is Hermitian as well. So gamma 5 is Hermitian, then also P left is Hermitian, because it's composed out of the unit matrix and gamma 5. So P left dagger is equal to P left, and then we have here gamma 0. Now again 20 seconds of time. What is that? Gamma 0, P left, gamma 0. Yep. It's P right because exactly. So that is the thing, and that is what I meant by the order matters, because you see, first to psi left, then U bar is the same as psi bar multiplied from the right with P right. And similarly, of course, psi right bar is equal to psi bar P left. And so there are textbooks which write things like this: psi left bar with a very, very short bar. That is an extremely bad notation, because it exactly does not tell you which of the two options it means. So if you see a textbook with this, then be careful. Okay, so but that is a relationship that is clear. And now let us also look at some terms in the Lagrangian. Our terms in the Lagrangian that we already know can be analyzed with respect to chirality. So let us analyze the known terms with respect to chirality. The most important term to create dynamics is the kinetic term, psi bar id slash psi. What happens if we analyze this term with respect to chirality? What we can do is, if it's not obvious, let us insert here at this point P left plus P right, which is 1. But then let's also use P left is the same as P left square and P right square. So we add here P right left square plus P right square. Then the thing splits into two terms, psi bar id slash P left square psi plus psi bar id slash P right square psi. How can we now continue to rearrange the term? Of course, P left square is P left times P left, and one of the two P left factors can be commuted around the P slash. So say P slash P left is equal to P right P slash, correct? Because the gamma 5 in the projector anti-commutes. So if we put it to the other side of P slash, the sign in front of gamma 5 changes. Therefore, we have some P slash times P left is equal to P right times P slash for any slashed quantity. So let us apply that here. Then we get psi bar P right id slash P left times psi. So one of the P lefts has gone to the left and has become P right. And here psi bar P left id slash P right times psi. And so then we can abbreviate using our previous abbreviations. So that thing here, psi bar P right, is the same as psi left bar times id slash times psi left, plus here psi right bar id slash psi right. So that means our kinetic term has been decomposed into terms containing chirality eigenstates. And what is the decomposition? We have one kinetic term for only psi left. Here psi left bar appears with the normal d slash operator. And the other term contains only psi right. So psi left and psi right, the two chirality eigenstates, they completely behave independently in the kinetic term. Let us compare that to the other term in the Lagrangian, which was the mass term m psi bar psi. What do we get from m psi bar psi? Let us again here introduce p left square plus p right square. Then of course we have m psi bar p left square psi plus m psi bar p right square psi. And then introducing the abbreviations, that simply means here psi right bar times psi left plus m psi left bar times psi right. So the mass term combines left and right chiral spinors, but the kinetic term does not. And that is interesting because it tells you that actually the left-handed spinors, they could appear just completely on their own, alone in the Lagrangian, if you only want the kinetic term. This kinetic term here, is that Lorentz invariant, by the way? Would it be allowed to write down only this into the Lagrangian? Or would it violate Lorentz invariance or something else? It's also Hermitian, clearly Hermitian. And it's Lorentz invariant because, of course, the psi left is a Lorentz invariant subspace. So that term is completely Lorentz invariant, and the second term is also Lorentz invariant. That was what I meant before, psi left, psi right. They do not mix at all under Lorentz transformations. Therefore, this left term is completely possible as a kinetic term in a Lorentz invariant Lagrangian. We could omit the right-handed term. And then we could completely omit the right-handed spinor field. But not if we want a mass term. So if we want a mass term, then we need the left-handed and the right-handed spinors. So that means that in the massless case of spinor theory, there appears an additional symmetry or an additional property, namely in the massless case where this term is zero, the psi left and psi right, they become completely independent. And you could omit one of them or take them both, doesn't matter, but anyway they are completely independent of each other. However, a mass term is something like a mixing between the left-handed and the right-handed spinors. I'll end with some nice conclusions on this. So Lorentz invariant and also dynamical theory with kinetic term is possible with only psi L, or of course only psi R. But this is only true if the mass is zero. Similarly, the fact with this kinetic term psi left, psi right, they appear completely independently. It also means something about interactions. Psi left and psi right could have different gauge interactions. So we didn't discuss that yet, but you know it from other lectures that the gauge interactions like electromagnetism, they are simply introduced by making the derivative operator into a covariant derivative, so they appear like the d slash in the previous equation. So therefore also for them psi left and psi right are completely independent, and therefore they could have different interactions. And that is the case in the electroweak standard model, where the interactions of the W boson and the Z boson behave exactly in that way, and they make use of this fact that left-handed and right-handed spinors can have different interactions, and they do have different interactions for the W and Z bosons. And then let me just summarize. And give you some new words that you can remember. So there are different types of spinors. And all of those different types of spinors are now understandable for you because of that discussion. So first of all, there is the Dirac spinor, which is what we have so far dealt with. The Dirac spinor is our familiar spinor. It has 4 complex components. When we look at the dynamical theory in the Lagrangian, then we get constraints. We get these canonical constraints on some of the canonical variables. And therefore, when we quantize, we do not get 4 times 2 degrees of freedom, but we only get 4 times 1, namely 4 degrees of freedom. 4 degrees of freedom, namely particle, antiparticle, and S equal plus minus 1/2. Those are the 4 degrees of freedom of the states in our quantum theory that we get after quantizing the Dirac spinor field. So 4 degrees of freedom and 4 complex components. Then there is the Majorana spinor. The Majorana spinor is simply a Dirac spinor psi with the additional constraint that psi is equal to its charge conjugated version. So that is a constraint, and yet another constraint in addition to those Lagrangian constraints, and therefore we reduce the number of degrees of freedom by 2. And I've shown you what that means on the level of the quantum field. C means A and B, the creation and annihilation operators are exchanged. Particle and antiparticle are exchanged. So if psi is equal to psi C, it just means that particle and antiparticle are one and the same thing. Particle is equal to antiparticle. That is the additional constraint. They are just the same states. And why not? Could in principle be possible. However, we are not sure whether such a particle exists in nature. The known fermions like electrons, top quarks, neutrinos, for most of them we know that particles and antiparticles are different, but for the neutrinos we are not sure. The neutrinos could actually be equal to antineutrinos, but they might also be unequal. So that is just an open question of current physics. And so maybe neutrinos should be described by such Majorana spinors and maybe not. And the last type of spinors are the Weil spinors. They are simply the left-handed spinor only. That is then really only this 1/2, 0 representation, or psi right only. And this is then really only the 0, 1/2 representation. So they only also have less degrees of freedom because of additional constraints. And so, for example, this psi left has then 2 complex non-vanishing components plus constraints in the Lagrangian. And if you quantize that one, then you get also half as many degrees of freedom. You get 2 degrees of freedom. But here particle and antiparticle is not the same. Instead, you only get 1 helicity. You only get 1 helicity corresponding to either left-handedness or right-handedness. So particle, antiparticle with mass 0, and here let me write it like this. The particle has only helicity minus 1/2, and the antiparticle has only helicity plus 1/2. And the mass is 0. So mass equals 0 means that the helicity is actually Lorentz invariant, and the particle appears only with helicity minus 1/2, and that then also explains the left-handed word. The antiparticle, however, only appears with helicity plus 1/2, and both are Lorentz invariant because the mass is 0. And so it could be that the neutrinos are also behaving like this. That is really this open question. It could be that neutrino particle and antiparticles are different. And then, as far as we know, the neutrinos, the neutrino particles, they appear only with helicity minus 1/2 in nature. Actually, what I'm saying is, of course, true only in the limit where you neglect the neutrino mass, but the neutrino mass is not 0. But if it were 0, which is a good approximation, then it could have been that the neutrinos appear only with helicity minus 1 and the antineutrinos only with helicity plus 1. Okay, so these are the 3 types of spinors, and with that we really stop our chapter on spinors first of all, and then tomorrow we will continue with the next step in our quantization, namely spin 1. Good, so see you tomorrow, and thanks for your attention.
طيب هنا أنا لدي أريد أن أتحدث عن ما ذكرته سابقا وأؤكد عليه. في هذه أين هي؟ عندما ذكر المحاضر في معادلة لاجرانج بأن طاقة الحركة تتصرف كل الجسيم، يعني الليفت هاندد والرايت هاندد يمكن أن تتصرف كل واحدة على حدة باعتبار الجسيم قائم بذاته، وتكون طاقة الحركة أو الانرجي تيرم اللي هو حد طاقة الحركة في اللاجرانج تكون لورنس انفاريانس، لكن الماس تيرم ليست لورنس انفاريانس. وهذا ما يؤكد على كلامي سابقا على انه البارتيكل والانتي بارتيكل عندما يتعلق بالامر بالماس فانهما يجب ان يكونوا موجودات مع بعض البعض. عندما يتعلق الامر بالماس فيجب ان يكونوا موجودات مع بعض البعض، كما في الكوارك والانتي كوارك. فإن البارتيكل والانتي بارتيكل تستطيع أن تفعل شيء للماس للكتلة، وبالتالي لا تشكل تهديدا إلى حد ما. أما في طاقة الحركة على هذه الجسيمات تسير في الماستر، هذه الجسيمات ساكنة، أما طاقة الحركة وهي تسير، فيمكن أن تتصرف الجسيمات كله على حدة، ليست هناك مشكلة في ذلك. طيب الشيء المهم الآخر هو أن هذه المعلومة قال لك سايرايد could have a different gauge interaction، خصوصا في الإلكترويك ستاندر موديل، بسبب أن الكتلة الماس يجب أن تكون الساي رايت والساي ليفت مع بعضهم البعض. فإنه بعد هذا ونجد أن الإلكترويك هي ذات مدى صغير جدا جدا. مع هذا عندما يتفاعل عندما تكون الكتلة صغيرة على الفضاء صناعي الأبعاد، فإنه يتم كسر هذه الكتلة بحيث أنه يجعل الساي ال والساي رايت تتفاعلان كل واحد على حدة بمعزل عن الثانية في الجيج في الجيج انفارس أو جيج ميكانيزم أو الجيج انتراكشن. لماذا؟ خصوصا في الإلكترويك، لأنه الإلكترويك هي تعتمد على صغر الأبعاد. يعني الإلكترويك هي تأثيرها 10⁻18. 10⁻18 هي الأبعاد التي تتأثر فيها الكوارك. تخيل أن لديك كوارك وأنتي كوارك متعايشان مع بعضها البعض في أبعاد في الإلكترويك، أثرت عليهم بطاقة عالية، سواء كان حركتهم وتصادمتهم مع بعض أو فهنا حصل طاقة إضافية وما كان يعني هي كانت مستقرة. الكوارك أنتي كوارك كان في اتصال مع بعض، هي مستقرة عن طريق الماس تيرم. أثرت فيها بطاقة إضافية، حركتها بطاقة عالية ثم صادمتها في بعض. يعني نمسك الميزونز، أنت صادمت ميزونات مع بعضها البعض بطاقة عالية، ماذا يحدث؟ هنا أنت أضفت كتلة إضافية للماس تيرم، بالتالي الفضاء ثنائي الأبعاد سيفعل دفاعه عن نفسه، سيدافع عن نفسه، وبالتالي تخرج جسيمات اللي هو الساي رايت والساي ليفت مختلفة عن بعضها البعض. وهذا ما يدلل على أنهما كل واحد لديها جيج انتراكشنز مختلفة عن الآخرى بسبب هذا الماس تيرم أو هذه الماس تيرم التي تعتمد على على هذه الخاصية الغريبة التي تعتمد على الكونفاينمنت، حيث أن الماس تيرم يجب أن تكون الماتر والأنتي ماتر مع بعضها البعض حتى يتم إلغاء الماس تيرم إلى درجة ما، لأنه بعد زيادة الطاقة فإن هذا الإلغاء لا يستطيع لا يعني يفعل. هذا الإلغاء لا يفعل عند زيادة الطاقة، وبالتالي الماس تيرم أو الماس ام تتغلب على هذه الخاصية الغريبة للكوارك والأنتي كوارك، وبالتالي يتم كسر هذا الترابط عن طريق الفضاء ثنائي الأبعاد غير المتناظر، وتخرج جسيمات أخرى. فموضوع الماس تيرم هذه في معادلة لاجرانج تتفق تماما مع الإلكترويك ونتائج الإلكترويك، وتتفق مع نظريته تماما. طيب في حالة النيوترينو، النيوترينو كتلته صغيرة جدا، فحالة النيوترينو الوضع يختلف، فإنه هذه الآلية وهذه الظاهرة لا تؤثر فيه، وبالتالي يعني كما ذكروا أنه يمكن أن يكون النيوترينو والأنتي نيوترينو في كتلة واحدة، ليست هناك مشكلة. يعني الأبعاد يمكن أن تصغر أكثر، وبالتالي يمكن النيوترينو والأنتي نيوترينو يكونوا مع بعضهم البعض. طيب تخيل أن النيوترينو لديه كتلته صغيرة جدا جدا. ذكرنا أن الكوارك والأنتي كوارك تستطيع أن يبقيان مع بعض حسب نظريتي، يبقيان مع بعض ليعادلوا الماس تيرم أو الماس يعادلوا كتلة، لأنه كوارك وأنتي كوارك كل واحدة لديها كتلة. طيب تخيل معي إن هذه كتلة صغيرة، فبالتالي وجود الكوارك والأنتي كوارك يمكن أن تصغر في الأبعاد. يعني يمكن أن الكوارك والأنتي كوارك تتقارب مع بعضها البعض إلى أن يأتي مرحلة كما يقال أنه في النيوترينو أن النيوترينو يحتوي على الكوارك والأنتي كوارك، قصدي المادة ومضاد المادة في شيء واحد اللي هي ما يسمى بمايورانا نيوترينو. طيب هذا شيء واحد. الشيء الآخر المهم جدا، إذا استطعنا أن نخفي قليلا من الماس بواسطة المادة والمادة المضادة في حالة الكوارك وأنتي كوارك، من باب أولى في حالة النيوترينو التي كتلتها أصغر، فإن التأثير هذا يكون مضاعفا. طيب إخفاء الماستر ماذا يعني أو الماس ماذا يعني؟ يعني تقليل التفاعلات المادية. كلما أخفيت الماس كلما سهلت صعبت التفاعلات المادية. وهذه خاصية إضافية يعطيها تعطى للنيوترينو بحيث أنه يجعله قليل جدا التفاعلات المادية، بالرغم أنه لديه كتلة قليلة جدا لكنه ضعيف جدا في التفاعلات المادية. يعني يمكن أن نقول خاصية المتر والأنتي متر التي فيها تقلل تأثير الماس أو تأثير الكتلة التي تحصل نراها في الكوارك والأنتي كوارك، فمن باب أولى ما يحصل للنيوترينو يكون أو يعطي من باب أولى أنه يعطي للنيوترينو هذه الصفة التي تجعله ضعيفا جدا في التفاعلات المادية، لدرجة أن النيوترينو يستطيع أن يخرج من الشمس ويصل الأرض قبل الضوء، أن يخرج من قلب الشمس ويصل الأرض قبل الضوء، لأن الضوء يتفاعل بواسطة الطاقة الكهرومغناطيسية، أما النيوترينو بواسطة الماتر والأنتي ماتر هذه يجعله غير قادر للتفاعل. وهذه حقيقة يعني أنا أريد أن أشدد عليها هنا بطريقة أكبر، أن النيوترينو كتلته أكبر من كتلة الضوء بقليل، فمن باب أولى أن النيوترينو يتفاعل من ناحية ماس كتلة، ومن وأقوى من ذلك من ناحية الكترومغناطيسي. فأي كتلة أكبر من كتلة الضوء ولو شيء قليل، يعني بشيء قليل، فإنه من باب أولى أنه يتفاعل بالكهرومغناطيسية أكثر من الضوء. الضوء يتفاعل بالكهرومغناطيسية، لكن من باب أولى أنه النيوترينو يتفاعل بالطاقة الكهرومغناطيسية أكثر من الضوء، لأنه الشحنة تتناسب مع الكتلة. لكن على عكس ذلك نجد أن الضوء يتفاعل بالقوة الكهرومغناطيسية أكثر من النيوترينو، وهذا بسبب خاصية المتر وأنتي متر موجودة في النيوترينو. ويدلل على هذه الكوارك طبعا يتفاعل بشكل أكبر من الضوء، وحتى أنه يتفاعل مع الضوء، لكن الكوارك يتفاعل في مساحة ضيقة جدا جدا 10⁻18. في هذا المساحة من باب أولى أن النيوترينو يتفاعل في مساحة أقل من مساحة أو في أبعاد أقل من أبعاد الكوارك والأنتي كوارك. وبالإضافة إلى هذه الخاصية التي فيها المتر والأنتي متر تغلق بعض البعض، جعلت النيوترينو لا يتفاعل كهرومغناطيسيا مثل الضوء يتفاعل كهرومغناطيسيا. فهذه خاصية غريبة جدا تفسرها نظرية عليسي، ويدلل عليها الكوارك والأنتي كوارك. طبعا هنا يشترط الكتلة تكون صغيرة، ويشترط أن خاصية أخرى، وهي أن المتر والأنتي متر من ناحية الشحنة تستطيع أن تلغي جانبا من الكتلة، وهذا ما يحصل في الكوارك والأنتي كوارك. طيب ماذا تاني؟ بالمناسبة لاحظ أن النيوترينو يتفاعل أيضا بالإلكترويك، النيوترينو يتفاعل أيضا بالإلكترويك، لسه الكوارك يتفاعل بالإلكترويك، فإنهم لديهم نفس الخاصية. يعني الكوارك يحمل الكوارك والأنتي كوارك، لابد أن النيوترينو يحمل النيوترينو والأنتي نيوترينو، لأنه يتفاعل بنفس الخاصية اللي هو نفس القوة اللي هو الإلكترويك، القوة النووية الضعيفة. فهذه خاصية أخرى جميلة جدا. طيب تاني ماذا؟ الشيء الثاني أنه في المحاضرات القادمة، في إحدى المحاضرات القادمة سيقول المحاضر أن الجسيمات تتفاعل أو الطبيعة تميل إلى الليفت هاندد في الانتراكشنز، تميل إلى الليفت هاندد في الانتراكشنز، لا تتفاعل بالرايت هاندد. لماذا؟ أيضا نظرية تستطيع تفسيرها. طيب لكي نفسرها تعال نرجع مرة أخرى. تعالوا هنا نجد أن موضوع الهيليسيتي والبوست، أن إذا كان الجسيم يتحرك ولديه كتلة فإن عن طريق البوست، يعني إذا كان هو ليفت هاندد مثل هذا السهم الأول، هذا السهم مثل هذا السهم، هذا طبعا الجسيم ليفت هاندد. الآن إذا عملنا بوست، بالنسبة للملاحظ عمل بوست وجعل حاول أن يجعل الجسيم هو نفس الليفت هاندد، سيرى أن الجسيم قلب حركته وأصبح ليفت هاندد لكن في الاتجاه المعاكس. ماذا يعني هذا؟ هذا يعني أن لا يمكن لإلكترونين أن يتشاركا نفس الطاقة إلا في حالة يكونوا متعاكسين بعضها البعض. أما إذا كانوا متوازيين فإنهما يتنافران مباشرة. ما الذي يجعل أنهم يتنافران؟ لأن الانتراكشنز تميل إلى تكون نفس الليفت هاند، نفس دعنا من الليفت هاندد، لكن تكون نفس الهيليسيتي. ما الذي يجعل ذلك؟ ما الذي يجعل الانتراكشنز تكون في نفس الهيليسيتي؟ هو أن نفس الآلية التي ذكرناها في المتر والأنتي متر. تخيل أن الإلكترون، تخيل أن البيئة الأولى هي الإلكترون، البوزيترون مباشرة البيئة الثانية التي تكون في معاكسة، تكون معاكسة لها طبعا. وإذا تقاربتا إلكترون وبروتون يحصل إلكترون وبوزيترون، أقصد بوزيترون أنا، فإنهم يحصل انتراكشن بينهما بالرغم من أنهما نفس الليفت هاندد، الاثنين ليفت هاندد، لكن نفس الآلية التي ذكرناها في الهيليسيتي يحصل ذلك. الأمر ينطبق على جزيء الهيدروجين أيضا أو على الإلكترونات في مدارات الطاقة. إذا كانوا نفس الليفت هاندد أو الرايت هاندد، نفس لفت الهيليسيتي، نفس الهيليسيتي، يجب أن يكونا متعاكسان. هذا التعاكس يجعلهم يشتركان في نفس الطاقة، مستوى الطاقة. أما إذا كانوا في نفس السبين فإنهما يتفاعلان مع بعض البعض. هذا ناتج من يعني تفسر نفس الخاصية الكوارك التي شرحناها قبل قليل، أن الكوارك والأنتي كوارك يستطيعان أن يتشاركان مع بعض البعض نفس الكتلة، أو أن يمحوان تأثير الكتلة. وبالتالي معاكسة المومنتوم، تعالوا نقول المومنتوم طبعا هو الستيت، معاكسة الستيت يكون بنفس الهيليسيتي، لكن إذا عكست الستيت فإنه يعني عكست المومنتوم، يعني عملت متر وأنتي متر، وبالتالي يتفاعلان مع بعض البعض، أو الماس تيرم تتدخل في هذا الأمر. الماس تيرم تتدخل في هذا الأمر. في حالة الإلكترون والبوزيترون الماس تيرم سيكون مضاعفا، لأنه كل إلكترون وبوزيترون كل واحد لديه ماس تيرم خاص به أو ماس خاص به، يكون مضاعفا. بالتالي تتغلب الماس على هذه المعاكسة الكوارك ولا أقصد المتر والأنتي متر، بالتالي يحصل تفاعل. في حالة مستويات الطاقة الأمر يختلف، لأنه مساحة أكبر، فإن المعاكسة في السبين أو في الستيت يجعلهم يتشاركان في نفس الطاقة. العكس المعاكسة يجعلهما يشتركان في نفس الطاقة. لماذا؟ لأنه مساحة أكبر. أنا أتكلم الآن عن مستوى طاقة حول النواة وليس داخل النواة، حول النواة، وبالتالي لدينا مساحة أكبر، وبالتالي يمكن أن يتشاركا وكأنما نيوترينو وأنتي نيوترينو، لأنه النيوترينو وأنتي نيوترينو لديهم كل كتلة قليلة جدا جدا بالنسبة لمساحة أكبر، وبالتالي يجعلهما يمحوان الكتلة ويجعلهما ضعيفة التأثير في التفاعلات المادية. أيضا في حالة الإلكترونات يمكن أن يتشاركان في نفس الطاقة إذا كانوا نفس مستوى الطاقة، إذا كانوا متعاكسان مع بعضهم البعض. أما إذا كانوا متساويان في أي شيء، فهنا يحصل انتراكشنز مباشرة، ويتحول واحد من الإلكترونات إما يتعاكس وإما أن يذهب إلى مستوى طاقة أبعد، بحيث أنه يبعد المسافة بين الإلكترون الآخر. ربما تكون الرؤية واضحة. يعني الكوارك والأنتي كوارك، هذه الآلية التي شرحتها سابقا تفسر لنا النيوترينو، تفسر لنا مستويات الطاقة، الإلكترونات تفسر لنا الانتراكشنز، لماذا الطبيعة اختارت الليفت هاندد، وهذا يضعنا في تساؤل. هل إذا وجدنا إلكترونات أو جسيمات كلها رايت هاندد هل تتفاعل مع بعض البعض؟ لأنه إذا كان كلامي صحيح الليفت هاندد، ماذا يعني الرايت هاندد؟ يجب أن تتفاعل أيضا. أقول الله أعلم، سأبحث في هذا الأمر، وإذا لم تكن صحيحا هذا الموضوع، فهذا يعني أن الرايت هاندد لديه صفة أخرى غير التي ذكرتها أنا تجعله غير قادر للتفاعل. هذه المعلومات مهمة جدا جدا. سأحاول أن أجعل اسم هذه الحلقة عن طريق يعني تحمل هذا المعنى، لأن الكوارك الأنتي كوارك أعطانا معلومة في غاية الأهمية بالنسبة للإلكترويك وبالنسبة للنيوترينو، لماذا جعل النيوترينو خاملا، وأيضا مستويات الطاقة للإلكترونات، لماذا كيف تتفاعل وكيف تشاركان نفس مستوى الطاقة، وأيضا كما سنلاحظ بعدين في الفيديوهات القادمة أن الانتراكشنز كلها تكون في نفس الهيليسيتي. السلام عليكم.